Morning, everybody. Welcome back. Let's see here. Tomorrow's lab is going to be our moment of inertia lab. That's a pretty big lab. There's lots of sort of measurements to take, and it does take a while. So do plan on being there for the full 2 hours and 50 minutes. And then hopefully we'll get it all done. And then we are... Let's see, so today finishing chapter 10, moving into chapter 11. That gives us Thursday and next Tuesday for chapter 11. Because Wednesday, next week's lab, what are we doing?
Review.
For your exam that takes place that Thursday, right? So I think I got that. Did I get all that right? Because isn't next week the week before spring break? Please say that it is. Okay, good. All right. Because I need spring break. All right. So that's where we're kind of at. You'll take an exam. Spring break will happen. You'll come back from spring break. We'll do an exam autopsy, move on to chapter 12. And, you know, being the final unit of the course. It's like, wow, it's crazy. It's crazy, crazy, crazy. All right. So let's finish up chapter 10. I flashed this picture on the screen last Thursday as a teaser, but what we're going to do now is we're going to use real pulleys. Up to this moment, the pulleys in all of our problems have done nothing except change the direction of the tension. They were always frictionless, massless physics pulleys. So what we're going to do now is we're going to keep the pulley frictionless. We could add in an extra friction on the axle, but it's not worth doing. All we're going to do is give the pulley mass, which means that as a pulley, it's going to have moment of inertia, and that moment of inertia needs to be dealt with when we've got connected objects. So in this course, this is the closest you will get to an actual real-life pulley and having to deal with all the complications of this setup. So you will, if you're an engineer, you will encounter this next in dynamics class, which is like a junior level engineering class. All right, so we got two objects and a pulley that we have to keep track of. The two objects, M1 and M2, this should be old hat. Like we should know how to deal with the mass on the hill, the mass that's hanging down. We've done this several times in our notes, so I'm going to kind of fly through these two masses and all of the forces that are acting on them, like the normal force, M1G. Let's put friction on the hill as this thing slides up. All right, so little change here from last time. I'm going to call this tension 1. What did we do before for the tensions on each of the objects? They were the same, weren't they? And the reason they were the same is because the pulley was massless and frictionless. Well, now that the pulley has moment of inertia and has a mass of all its own, and it's going to take some torque and some effort to get the pulley to rotate in and of itself, we can no longer say that those two tensions are the same. So we're going to keep those two tensions separate. I'll just come in here real quick since I'm here, and I'll go ahead and find these components, which again, we know M1G cosine theta, M1G sine theta, and we will make up the slope be positive x, and away from the slope be positive y, and well, assuming if there's any acceleration, it will be up the slope. So I think I got everything there. If we go to mass 2, we have gravity pulling it down. We have a tension 2 pulling it up. Acceleration's down, so I'm going to make positive y be down. Again, the only change from before is that these two tensions are no longer the same tension. They are different tensions. All right, so then we come over here, and we're going to write down x and y directions for mass number 1. And for mass number 2, we'll do the same thing. Mass number 2's x direction is pretty easy. Always seems to be that. All right, so let's see. M1A equals, in the x direction, what have I got? I've got T1, I've got F, and I've got M1G sine theta. So let's get those all in the right order and direction. You grade me. How did I do there? Why is T1 positive? Up the slope, and it's the direction I called positive, right? So that means F and M1G sine theta pointing down the hill are going to end up negative. Did I get it right? Yeah, I got it right. So pretty satisfied there. In the y direction, n minus m1g cosine theta. I've only got this force and this force to deal with in the y direction. Okay, m2 bog standard m2a equals m2g minus t2. All right. So again, that mostly flows from stuff that we have done before. Really nothing new in there. Now, what we have to do is we have to deal with this pulley. And this is kind of the new part for chapter 10, right? Is this whole concept and idea of torque and how it's applied to objects and things like that. So what I've done is I've taken this pulley, and it gets a little bit confusing if like I try to draw everything up here on this thing. So what I did is I took this pulley, I enlarged it, and I've got sort of a new diagram over here, right? So we're gonna try and keep track. We're gonna draw our free body diagram of our pulley down here. First thing that I am going to do is I'm going to set my coordinate system. So because I said acceleration is positive up the slope and down, right? I've got this change in motion that's happening up the slope and down. I'm kind of forced into choosing a direction for alpha for the rotation of this pulley to be consistent, right? If I say acceleration's up the slope and I say it's down, what do I have to say in terms of clockwise and counterclockwise for the pulley? Which way is going to be positive? Clockwise, right? Because I've got this, I don't want to confuse my equations and get directions backwards from what I've specified. Up the slope and down is going to result in a clockwise rotation of this pulley. So I'm going to go ahead and say, well, because I guessed my accelerations for the other two, I'm going to make sure I understand that my acceleration has to be consistent, right? And then that means that I'm going to make clockwise be positive. Again, I tend to use a little symbol. Sometimes I put CW for clockwise and CCW for counterclockwise. All right. So this is in rotation. We've got to ask ourselves the question, are there any torques on this pulley? Yeah. If this is my pulley right here, okay, then I've got a force that's kind of being applied on this side, don't I? And a force that's being applied over here. So there's definitely torques. Question is, which way are the directions of those forces? Does everybody agree that the one over here on the left is going to be T1? Right? That's coming from mass number 1. We said mass number 1 is getting tugged up by tension 1, right? So think Newton's third law. Maybe sing a song. If the pulley pulls on the box, then the box pulls on the pulley, and we know from Newton's third law, those forces have to be the same magnitude, but opposite direction. So if the box is being pulled up, what is the pulley being pulled? Down. And which way is down in this picture? Yeah. The tension 1 is going down like that. Now, the pulley is rotating clockwise, but the force T1 is pulling down on it. If T1's pulling up on mass 1, it has to be pulling down on the pulley. And by a similar set of conceptual steps, we know that tension 2, right, is being pulled up. It's supporting mass number 2. So what direction is tension 2 acting on the pulley? Down. Again, Newton's third law, keeping the directions consistent and all that kind of stuff. Notice I mentioned up and down and left and right and down and up the slope. I wasn't referring to like the ways that I defined things to be positive, right? I'm defining positive directions as up the slope, clockwise rotation, and down. But when I did my analysis for the tensions and the directions those tensions were pulling, none of that mattered. All that mattered is I looked at the two objects that were interacting and made sure that they were pushing and pulling on each other, right? Equal and opposite forces. All right. Well, those are forces. They're not torques yet. What do we need in order to have a torque? We have to have like a perpendicular distance, right? Because a torque is a distance perpendicular to a force that's acting. Well, luckily, we've got a circular pulley, which means that no matter where the tension comes off, there's always going to be a perpendicular distance to the axis of rotation, and it's called the radius of the pulley, even if I draw mine sort of crooked. Oh well. Okay, so what are we doing for the pulley? Let's move that up here, okay? So for the pulley, there's only one dimension, the dimension of torque. There's no x, there's no two dimensions, right? The thing is, the x dimension has two directions. The y dimension has two directions. Well, the torque dimension has two directions, clockwise and counterclockwise, but there isn't like another axis to that. So there's really only one equation that we have to write down. And that equation is Newton's second law in rotational terms. Does anybody remember what that looks like? MA equals sum of the forces, or I alpha equals sum of the torques. And again, this is sort of our new frontier that we're moving into in this chapter. So it's m times a, but the rotational versions. So rotational mass times rotational acceleration equals, and then I have to write down how many torques that I have. I really suggest that for this step, so you can just automatically, as a template, right, just write down I alpha equals, because the physics part, okay, comes in determining what the torques are. So for determining the torques, my suggestion is you break this into 3 steps. In the future, maybe you'll be, good enough to put some of these steps together. But it really helps you to not miss things and to keep track of stuff if you break this part into 3 steps. First step, how many torques are there? What's the answer? There's 2. Why is there 2? There's 2 forces, right? Okay. So I know that there's going to be a torque. Leave a little bit of space. A torque from T1 and a torque from T2. I'm leaving space in between, okay? For the second step, where I'm going to come in and I'm going to try to determine whether the torque is positive or negative. Now, the only way I can know if a torque is positive or negative is by having a definition for what positive is, right? So what's positive? Clockwise, right? Clockwise is positive. So I now need to determine which of these torques, right, is positive or negative. And I taught you a little trick about this one if you're having trouble just sort of seeing it. And some people can. Some people look at that and go, oh, I know T2 is positive. But if you're having trouble with that, remember the pencil trick, right? What you do is you kind of hold up your pencil, right, to your page, grab your pencil at the axis, like where it's going to rotate around, right? And then just line up your pencil with your radius, grab your pencil tip and pull it in the direction of your force. Right? If I land on my pencil and I pull it in the direction of my force, which way is my pencil rotating? Clockwise. So what are we going to call that torque? Positive. So wherever the T2 is, torque from T2 is going to be a positive torque. Okay, now we do the same thing for T1, right? I hold my pencil up, I grab it in the center of the pulley, kind of angle it up in the direction of R. I come up here, I grab and I pull in the direction of T1. Which way is the pencil rotating? Counterclockwise. So what are we going to put on for the sign? Negative. So we're going to use that trick moving into chapter 12, 11 and 12. So that trick's not going away. So do kind of practice that a little bit. It's a good way, right, to see which way it's going to rotate. And depending on what you've said is positive, clockwise or counterclockwise, you got to assign the signs. All right, so what we've done, we broke it into 3 steps, but we haven't done the 3rd step yet. First step, just write down the torques. List out all the torques you've got, leaving spaces in between. Then go through and figure out the directions of the torques, positive or negative. Now, the 3rd part is we actually write down what the torques are. A torque is a distance perpendicular to a force, right? So we need both of those things. So now what I'm going to do is I'm going to come down a line. It's going to be negative, and now I want to write down what that torque is, right? So what is the distance to tension 1? Just R, right? The radius of the pulley. So R, and then what's the force? T1. Not bad, right? Plus, and then what's the perpendicular distance to tension 2? It's also R. And T2. So there's a 3-step process, right, that happens in here. 1, identify all your torques. 2, assign their directions. And then 3, write R perpendicular to force, right? Whatever your perpendicular distance is, whatever your forces are, go ahead and write them in. All right. That leaves us with, what have we got? We've got, I'll do them in green. We've got that equation right there. That one. Don't make it go away. That one, and that one. Remember, Newton's second law is like an equation generation machine. I don't know what F is. The friction. But what am I going to remember? You said it, not me. There's another one. Well, how many equations are there? 1, 2, 3, 4, 5 equations. Oh my gosh. How many unknowns do I have? I don't know. Does it matter? I don't know T1. I don't know F. I don't know N. I don't know A. I don't know T2. 1, 2, 3, 4, 5 unique unknowns. 6 and maybe 7. I have 5 equations and 6 unknowns. Is it possible to solve yet? No. So I need another equation. Oh my gosh. This is so bad. Okay. The way we're going to get there, there's definitely a difference between the equations up here and the equation down here, right? One's written in angular terms, one's written in linear terms. So we should try to, is there anything that's like connected or the same? The obvious ones are T1 and T2, right? Okay. So if we're going to find let's say we want to find the acceleration, okay? We're going to find the acceleration of the system. Well, it's up there, it's over there. Oh, can those accelerations be the same if the tensions are different? The only thing that would change acceleration is if the strings were stretching or breaking. So they're still physics string. Okay, we haven't included the mass of the string, and we never will in this class. Okay, but acceleration is the same. So what does that mean for alpha? Is alpha connected to A? Google Translate, right? So what's the Google Translate between A and alpha? The tangential acceleration was equal to r alpha. So there it is. There's my sixth equation. Oh my gosh. What do we do about the moment of inertia? Yeah, right? If we're told something about the pulley, like its mass and its radius, then we can go here and look at the chart, and which of these things is most like a pulley? It's probably that one, right? Pulleys tend to be solid all the way through. If they're not, they have spokes, and then you want to cry and all that kind of stuff. But generally, pulleys will be that thing right there, unless you're told otherwise. There are spherical pulleys. They're weird. They can go in more than one dimension.
So you said the acceleration will be the same throughout?
Yes. Yeah. A is alpha. Well, A and alpha are related to each other right there, right? So this A is that A, right? All right. We've got enough equations. 6 equations. We're gonna do our moment of inertia is 1/2 mass of the pulley r squared. Oh my gosh, what do you do? ChatGPT. Wolfram Alpha would be better. Yeah, so tensions are so I'm not going to do all of this because we've got better things to do with our time than a whole bunch of algebra. Okay? And the whole point of this example was to show you how to deal with this pulley and write out this equation right here, right? The other thing I wanted to impress upon your minds is just be careful when you start saying, well, what about the real pulley, Mr. Balogh? Well, this is what happens. Why did we not do real pulleys back in the day? Yeah, how many of you would have dropped if I dropped this on like chapter 5? Right? Now you're trapped. You can't drop anymore. No, it's just that as you start adding friction, as you start adding mass to pulleys, as you start stretching strings, by the way, if you start stretching strings, you start developing differential equations, right? So you got your diffie-q's need to get involved. It goes bad fast, but the amazing thing as humans is that we figured it out and it works. So as an outline, I'm not going to show you I'm not going to actually do all this math. I would solve for n, plug it in there. Solve for f, plug it in there. Solve this for t1, plug it in there. Solve this for t2, plug it in there. Solve this for alpha, plug it in there. Put my moment of inertia in there. And what I end up with should be an equation that has nothing but a's in it. And there'll be a's everywhere. Okay? But then it's a matter of algebra to factor all those a's out, right? Blah, 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 and get down to it. Okay? It's been done. Let me prove it. Come on. Modern technology for the win. Here we go. Yeah, use that picture. So here, you can't quite see it yet. Let's make sure we get the whole thing fitting on the screen. It's good enough. Okay? So I included all the work. You guys can check and see if my math was bad or not. I have a tendency to skip steps and things like that, but you can see my pulley thing. It looks like I've got all my directions the same. Anyway, the thing that you end up with in the box is the acceleration. Now, can you copy this onto your cheat sheet and use it on the exam? You could, if and only if what is true? Everything is exactly the same, right? The problem with Newton's second law is it's an equation generator for whatever situation you are presented with, right? And you need to generate new equations if the situation changes, right? If this thing were sliding the other way, for example, that would be a different situation. Probably some minor adjustments, especially in the direction of the friction, and there might be a sign switch here and there. But you really want to attack each new situation with fresh eyes. Don't just rely. This thing in the box up here is only for this situation, for this very specific set of circumstances. And your homework has different circumstances. But the process, the way that you go about generating the equations and then the thing you have to do is the same process. Write down your linear equations for whatever masses you have in the problem, and then write down a torque, angular Newton's second law problem for the pulley, and then find how all the things go together. The problem could be asking you for tension, right? In which case you want to eliminate the acceleration. Eliminate all the things you're not given. Solve for the thing you're asked to solve for. And your life will be miserable in algebra, but you'll get through it. You will. It'll be okay. This is the final example for chapter 10. Okay, again, just trying to give you more experience with writing down Newton's second law in its rotational form. Looking at this problem, I can tell you right now, I'm going to have Newton's second law in its old-fashioned chapter 5 and 6 form, and I'm also going to have it in its rotational form. How do I know I've got a linear version? What's like the giveaway in the picture even? There's a box hanging down right here, right? How is it going to move? Probably going to come down, isn't it? It's going to move straight down, isn't it? So that's definitely a Newton's second law linear equation, right? Ma equals F. But as it moves down, it's going to rotate this thing that it's attached to. And so I'm going to have a rotation, right? So look for things moving in straight lines to know when to apply Newton's second law in linear form. Look for things that are rotating in order to know when to apply Newton's second law in its rotational form. Okay? So let's start with mass number 1. We got to get free body diagrams of everything we can. We can definitely do a free body diagram of mass number 1, right? And I'm going to assume, right, that this thing is accelerating down. It doesn't really say, does it? It doesn't say if mass 1 is falling, right? It just says it's attached, and it's. I'm just going to guess that mass 1 is pulling down. If I get it, if that guess is wrong, I'll get a negative number for my answer, and it'll just mean it was going the other way. I'll get the right magnitude. Okay, so that means I'm going to make down be positive. So in making down positive, which way am I going to make rotation positive for the wheel? Or the reel. It's not a wheel, it's a reel. So I'm going to make whatever this direction is be my positive, and that looks like a counterclockwise direction, doesn't it? Okay. Now I've got to come in and look at this reel thing that I have. Maybe this is a fishing reel or something like that. I don't know. Okay. What do they tell me about? It's got an outer radius r. So like it goes, I should have drawn that somewhere else. It's got an outer radius r, and it's got an inner radius of little r. It's got some mass, okay? Ooh, what are they? They said it's a hollow cylinder. What are they trying to tell me? Right? So, yeah. Probably this one, right? So we'll come back to that. Oh, geez. Friction. Where does that friction act? The question isn't really clear, but I believe that this thing in here is the axle, right? That the reel is like all of this material right here, right? And that this is the axle that it's sitting on, which means that the friction exists all around here, doesn't it? Okay. And it's kinetic friction because apparently the reel is just sliding on this axle. But what direction is the friction acting? It's kinetic friction. So opposite the direction of motion, right? We said we think it's accelerating. We think it's increasing its speed in the counterclockwise direction, which means that its speed, like, I can just imagine that if I just like held this here and then let go, gravity is going to pull this thing down, right? It's not going to like wind it back up. Whoops. Okay. So gravity doesn't work that way, right? There's no other force that's winding it up. So I think it's safe to say this thing's going to, if not accelerate, it's at least going to move downwards, right? So the motion of my reel is going to be counterclockwise. So that means that the torque from kinetic friction has to be which way? See, I already confused everybody because I don't know how to ask questions. If the wheel is rotating, did I get that right? Is that counterclockwise for you? Okay. If it's rotating counterclockwise as this mass pulls it down, right? The friction in here, in the hub, on the axle that it's sitting on, has to apply what kind of torque to slow this thing down? It has to be clockwise, right? The wheel's going counterclockwise. And I need a clockwise torque to get it to come to a stop, right? It's kinetic friction. So it's acting against the direction of motion. So now the question becomes, how the heck do I get a clockwise torque out of a friction? I know the friction's only acting on this surface right here, right? All over that surface. But what I want to do is I want to take a look at just one spot, right, on that surface and see the direction I need friction to be in order for there to be a clockwise torque. So if I take like this bottom point right here, okay, how would I get a clockwise torque? What direction would the friction have to be at this point to cause a clockwise torque? It's not going to be tangent. It's not going to, it's not going to be like in or out, right? Those directions can't cause torques. But those two directions can. And of those two directions, which one's going to make it spin counterclockwise or clockwise? Right. It's that one, isn't it? Okay. If I'm over here, it would be down. If it's over here, I would be up. But if it's here at the top, it would be to the right. All of those frictions, right, are causing a clockwise torque. Again, hold your pencil at the axis of rotation, go to the point that you want, figure out which way you have to like push or pull to get this thing to go clockwise. I got to pull to the left to get it to go clockwise, right? If I'm on the side, I have to push up. If I'm at the top, I have to push to the right to get it to rotate rotate clockwise. So I know I can just pick one spot. It doesn't have to be everywhere. I can just pick this spot and realize, okay, my kinetic friction has to act that way. And again, this torque, this little r times this f, is going to counter this big R times this t, which I didn't draw. T would be acting down. So let's do that one. Big R, right? T pulling down causes what direction of rotation? Counterclockwise, right? So we're countering that with a torque from the friction. And I know I have to counter it because it's kinetic friction. Kinetic friction always acts against the direction of motion. Okay, I I think I've got all the pieces parts. I'm going to redo these at a different color here so it's a little bit more consistent. So I think I've got all of these different parts set and ready to go. We're about to find out. But I specified directions. I've got my forces labeled, coordinate system. There could be things I'm forgetting, but you know what? We'll figure it out when we get there. So let's see here. Newton's second law. In rotational terms, some of the torques. And Newton's second law in its linear form. All right. Okay. What do you want to do first? Rotational or linear? Rotational. All right. Let's just jump right in. See what we get. Okay. They told me it's a hollow cylinder. So we're going to use 1/2 m and then the sum of the radii squared. So the moment of inertia, 1/2 m2, and then it's going to be r squared, little r squared plus big R squared. So there's my moment of inertia times my alpha equals, okay, 3-step process. What's the first step if we're trying to identify torques, sum of the torques? Write down your torques first. Just get them on paper. How many torques are there? 2. There's a torque from the tension, and there's a torque from the friction. Okay, second step, what are we going to do? Yeah, figure out the directions that they're going, right? So, torque due to big T. Pencil, pull down, rotation is which way? Counterclockwise, and counterclockwise is what? Positive sign. And then the friction, we already established all this, but it's good to check. Pull to the right, causing a clockwise rotation, and that will be negative. Okay, now that I've done those 2 steps, I can now do the next step and write down, I got to copy this line down here, alpha equals, and now I can write what these torques actually are. Remembering that a torque is a distance perpendicular to a force. So my torque, my distance, it's going to be, I'm talking about big T, so I know that's going to be my force, but what's the perpendicular distance from the axis of rotation to big T? It's big R. So it's big R times big T minus, and then the friction is acting at little r times my force of friction. Okay, we're looking for the acceleration of the hanging mass. And that's not in there. Well, it's kind of hiding. You know where it's hiding, don't you? Where's it hiding? In the alpha, yeah. Because we're going to have to do A equals R alpha. So alpha is going to be A over, what R do we put in? Yeah, it's big R. We put in big R because the acceleration of the hanging mass is related to the angular acceleration at the outer edge, right, of the wheel. So we better be really careful there and put in big R. All right. So that again can get substituted into there. Okay. Now we can go do our hanging mass. This one should be pretty straightforward. MA equals what? M1G minus T. And see how we kind of are sort of at the level where we can kind of put the signs and the forces all right down there because we've done it so much, right, and so often. So, all right. Where do we go from here? Good grief. What do we know? I'm going to assume that, like, if they say M1 and big R and little r and M2 and F, those are all would be like numbers they would give me. Okay? I wrote the problem, so I'm saying that's the way it is. Okay? So I know F, I know R, I know big R, I know all of this. I know M1A. Well, I don't know A. I know M1G. So really, kind of the outstanding thing that I don't know is the tension in the string. They didn't give me tension in the string. So what does that suggest as far as like a algebra method to employ here? Yeah, solve for a t and then substitute it in so we get rid of it, right? We don't want to know it. We want to get rid of it. So that's exactly what I'm going to do, right? So this one is t equals m1g minus m1a. I swap positions across the equal sign with the t and the m1a, so they get to swap signs too. That t is now going to get inserted into there. Equals a over big R equals, and now it's going to be big R times all of this mass m1g minus m1a minus R times F. So what I've got now is I've got an A here and an A there. So I've got to work all of that stuff out, right? You know what? To make my life just a little bit easier, I'm going to move this back to I. Do I know all of these numbers? They gave me M2 and they gave me the radii. So the answer is yes. I know all those. It's just a number. And I don't want to have to carry around big things that are just numbers. Rm1g minus Rm1a. I just multiplied through over there. So now this is going to be the Rm1a comes over here, and I factor out my a. That leaves me with I over R minus plus Rm1. Kind of doing a lot of math in one step there. Rf, and then I can divide both sides by that thing that's next to the a's. And I get I over R plus big Rm1. Yep. And that's what's in my notes. And we will call it good. Again, if I had numbers in there, the numbers would probably be easier to do than all the symbols. Whoo! It's fair to say that torque is like peak difficulty for this unit. So far in this unit, what we've done is what? We've done kinematics, but in circles. We've done energy, but in circles. And now we've done forces, torques, forces in circles. What's the only other toolbox we have left? Momentum. So what I need to do now is we need to transition into chapter 11, which is all about angular momentum. Okay? However, to be able to talk about angular momentum, for the last time, I've got to teach you more about vectors, because there's one kind of multiplication that we're going to need that we haven't talked about when it comes to vectors. What was the multiplication we did way back in, was it chapter 7? It was the dot product, okay? Although otherwise known as the scalar product. And what it gave us was beautiful. It gave us not a vector, right? It gave us a scalar thing. And remember, the cross product was out to, the dot product was out to answer a question. The question being, how parallel are the two vectors that you are multiplying together? Which seems like a weird way to talk about multiplication, but nonetheless, things that were perpendicular in dot products always gave you what answer? 0, right? And so you know if you had 0 from a dot product that your vectors are perfectly perpendicular, which is nice. And if you got the maximized value, it means that they were perfectly parallel. Again, nice information to have. But in order to introduce you to the cross product, which is the other form of vector multiplication, I do need to talk about the vector directions for rotating quantities. We've already done one of them. Find the direction, the vector direction of the angular speed for this wheel. Do you remember how to do that? Yeah, it's a right-hand rule. I saw some of you go for it, right? Remember the hitchhiker right-hand rule? What do you do with your fingers? You curl them or wrap them around in the direction the wheel is spinning, and your thumb points in the direction of the angular velocity, right? So that if I spin this the other way, now what do? Like that, right? And it points now towards me. And I can do it like this so that it's pointing down, right? If I turn the wheel over, I use my right hand, right? And it points up. Okay, so we can find the direction, the vector direction for angular velocity. Up to this point, I've been hiding something from you about torque. I kind of told you about it, and then I very quickly distracted you with something else to alleviate the pain. But now the pain begins. Because torque isn't just that simple thing that I've been teaching you about, r perpendicular to f. Torque, by definition, is the vector cross product between a lever arm, a moment arm, a distance from an axis of rotation, and the force that is being applied. Notice in this statement, when we are multiplying r and f together, torque has a vector arrow over the top of it, doesn't it? So the cross product, and why is it called the cross product and not the dot product? It's the multiplication symbol that matters. If you're multiplying two things together, right, just sort of that A dot B sort of thing, right, okay, that vector multiplication gives you a scalar, right? Whereas over here, we have to get another vector out. If I come up to this wheel and I apply a torque to the side of it, okay, my lever arm, my distance, starts from the axis of rotation and goes all the way out to where the force gets applied. My R is to the left. Left for you guys? It was left, right? And my force is being applied upwards. But so I've got two vectors there. I've got the vector coming out from the center to where it's applied. I have the vector acting upwards. But then the torque is a third vector that turns out to be perpendicular to both r and f. What does the cross product give you? Those of you that have had cross products before. The vector that you get out of a cross product is perpendicular to which one? Both of them simultaneously. Oh my gosh. My brain already hurts and I've got a propeller on my head. All right. It's a cooling fan. Let's say that we had a vector that was like that. I don't know what it is. It's just there. Okay? And let's say that I had, I don't know, another vector that was like that. Okay? Now, those two vectors aren't perpendicular to each other, right? There's some angle between, I don't know, whatever, okay? But there is another vector that is perpendicular to both of them at the same time. Let's back up. It can be hard to see for the first time. Get rid of that one for just a second. Okay? How many vectors can I draw that are perpendicular to this one? It's not 1, it's not 2, it's not 4. It's infinitely many. There's an infinitely many vectors that are perpendicular to this one. Do you agree that this is a perpendicular direction? And what about this one? What about this one? What about into the board? And everywhere in between, right? I can describe an entire plane, right, that is perpendicular to that vector. So, if you have one vector and you say, oh, well, what's perpendicular to that? The answer is yes. Okay? Now I have my other vector. That one. How many vectors are perpendicular to that one? And infinitely many, right? Be down here, over here, right? There's a lot of vectors that can be perpendicular to that one. But there are only 2 vectors that are perpendicular to both of these vectors at the same time. Think of it as the meeting of where the 2 planes of infinite numbers of vectors come together. What do you get? What's the geometrical object when 2 planes intersect? It's a line, right? So to be perpendicular to this one and be perpendicular to that one simultaneously, what are the only 2 directions that are going to work? Out or in. That's it. Those are the only 2 directions that are going to be perpendicular simultaneously to those 2 vectors. If I had 2 vectors in the plane of the table, don't draw on the table, okay? Right? But I had 2 vectors in the plane of the table, what's the only directions, the 2 directions that are perpendicular to 2 vectors that are in the plane of your table? Up, away from your table, and down into the table. The good news is you got a 50-50 chance. Okay? The bad news is that we have to introduce another right-hand rule in order to figure out which one of those is the correct answer. But let's jump into the mechanics of the cross product, the mathematical mechanics of the cross product first. You are going to have a question on your exam that is basically here. This has been a theme on all your exams so far, right? Make sure you know how to add vectors and subtract vectors. That was the first exam. This last exam was, can you do dot products? This exam is, can you do cross products, right? Just a strict, straight up, mathematical, giving you 2 vectors, find the cross product. So you're going to want to learn how to do this, okay? So okay, so what are we doing? We are going to do 2 vectors, Alfred and Beatrice, okay? And we're going to find their cross product. Now, there's an algorithm here that will help you find the cross product at any time and at any point. And I really strongly suggest that you learn the algorithm I'm about to teach you. At the end of the algorithm, there is an equation, just like a function that you can plug stuff into if you want, right? So if you're really struggling, you don't understand the algorithm, that's okay. If you get the punchline down, you should be mostly safe, okay? But the problem is, there's many ways to go about doing this. Your math teachers might have taught you one thing. I'm going to teach you this, right? It can sow a little bit of confusion. But let's do the full algorithmic way, literally turning a crank on what's going on. And what you're going to do, you're going to make a little spreadsheet. Now, all the mathematicians just died because I referred to a matrix as a spreadsheet. But that's what a matrix is, okay? It's a spreadsheet, right? And what is your matrix going to look like? Okay, well, the symbol for a matrix is big lines, okay, on either side. You are going to write down, this always looks like this, I hat, j hat, and k hat as like the column headers, the labels on your columns. And then the middle row, the second row, is going to be the components of your first vector. And I'll give you one guess as to what the third row is going to be. Yeah, it's just going to be all the components of the second vector. Order does matter. The order that that cross product is happening, A cross B, is not the same as B cross A. B, Y, B, Z. Okay, so what you've done here is you've laid out, you've made a spreadsheet. Okay, it's got 3 columns, it's got 3 rows. If you want to think of it as tic-tac-toe or something, that is totally up to you, right? But you've got to lay it out just like this. And then you are going to run an algorithm. You're going to do a pattern through this matrix that's going to generate the answer for the cross product for you. You're going to start with I hat. And what you're going to do is you are going to cover this column up. Don't erase it. Do this in your mind. But you're going to cover up the I hat column. It seems kind of weird, right? You're looking for I hat. You want the X component of this cross product, but you're not going to use any X components in making it. So you're going to cover up with your eyeballs, with your hands, with your fingers, something. You're going to cover up the I hat column. You're going to concentrate on this little 2 by 2 portion of your spreadsheet. You're going to multiply across a diagonal and subtract off the product of the other diagonal. So again, cover up, look at what's left, top left to bottom right, bottom left to top right, taking the difference. So I'm going to write that down right now. That would be, AYBZ, right? Cover this up. AYBZ, that's the product that's sitting right there, minus, and now I'm going to do BYAZ. The actual order of the thing in the product doesn't matter. You just got to make sure you get the subtraction in the correct direction. All right. And that's the algorithm you are going to repeat for the other directions. Only, caveat, you have to do minus j hat. Do not ask me why. I do know the answer. I didn't know the answer for the first 20 years of my teaching. Students would ask me, why is it negative j? I'd be like, ask the math teachers. Okay, I don't know. It just is. It's good enough for you to know that it just is. If you want to know the answer, we're going to end up in n. It's not one-dimensional, two-dimensional, three-dimensional. It's n-dimensional space with something called a quaternion, which is like a n-dimensional vector. And it gets kind of weird, but it's actually kind of beautiful. Math can be pretty beautiful at some points. I don't like it, but it can be beautiful. Okay. So just remember, it's I minus j plus k. So, okay. So for the j stuff, what column do we cover up according to the algorithm? Cover up the j column, right? We're going to ignore it. We do the same 2 by 2, right? AXBZ, subtracting off BXAZ, right? AXBZ minus BXAZ. Again, right, I covered up j. I went AXBZ for that one. And then I wrote down my minus sign. And I came over here, BXAZ, to come up with that one. It's a pretty simple algorithm. I tend to remember algorithms better than I remember actual equations that come out. And so I can always redevelop this one at any time. The other kind of cool thing is, look at what you're looking for. I'm looking for an X component, I hat. There should be no X's anywhere in this. That's how I know I didn't screw up too badly, right? over here with the y component, notice how there's no y's going into it, right? It's kind of a dead giveaway that you might actually be doing this correctly. Plus I minus j plus k. What column do we cover up? Cover up k column. Leaves this 2 by 2. We go down that way, subtract off that way. So it's going to be axbz minus bxaz. So is this how they teach it to you in Math 6? No? No? Okay. I apologize. I should probably go find a Math 6 teacher and pin them to the wall and figure out what they do. What? Yes. See? I didn't go back and check. These should be y's. Regardless of how they teach it, it should come out the same. Because I know there are different methods for doing cross products. This is the one that is favored by physicists. This is the one I see quite often in physics textbooks and things like that. So the good news, this is the answer. Well, I don't know if that's good news or not. That's a terrible answer, isn't it? But like, even if you can't remember the algorithm, if you write that down, you'll be able to find the cross product between any two vectors if and only if you know their components, right? You have to know the x, y, and z components of these vectors in order to be able to do this. Okay. I'm going to do some examples with numbers in them here in a bit. So just hang on, okay? Fortunately or unfortunately, I'm not sure which, there's another way to do cross products. And this one is definitely more conceptual. Requires a right-hand rule and some ability to visualize things, but mathematically it is more straightforward. Okay? Like it's easier to calculate. So the other way to do this, right? You can find the cross products between two vectors if you find the magnitude of the cross product, which turns out to be magnitude of A, magnitude of B, sine of angle between them. Now that's a magnitude, that's not a vector, right? It's just a number. The tricky part sometimes is figuring out what the angle between them is, especially depending on how they give you vector angles. Just make sure this is the angle between the vectors. So like I don't know, as an example, if you had, say, a vector at 90 degrees and another vector at, 60 degrees, what's the angle between those two vectors? It's 30 degrees, right? You're not putting in 60, you're not putting in 90, you're putting in 30 degrees. So just be careful, right? Make sure you understand which angle you are using when you calculate it this way. Generally in physics, we try to make those angles 90 degrees because the sine of 90 is 1, right? All right, so you can, but that only gives us the magnitude of the cross product. The direction for the cross product is given by the right-hand rule. And this is a new one. Because in this course, up to this point, we've had hitchhikers, right? Now, what we are going to do is we are going to do handshakes. Okay? So there's a difference in my mind between the shape of your hand if you've got the hitchhiker. When you're doing the hitchhiker, your fingers are curled into your palm, right? And that suggests that rotation that we've been talking about. But a handshake has you extending your fingers out straight, right? And so that's how I distinguish these two right-hand rules in my head. I use a hitchhiker in rotations, but I use handshakes when I'm finding cross products. Because cross products come from straight things, right? My hand is straight, and I'm going along straight vectors. Again, there's different forms of this right-hand rule. There's the way I'm going to teach you with the handshake. I'll teach you also one that has you holding your hand a little bit like this, that looks like a gun or something, pew pew, right, whatever, right? Violent imagery, welcome to America, okay? There's another one that you hold, like the palm does something. I don't teach that one. It generally confuses people that I've noticed, okay? Those of you that have Math 6, how do they teach you the right hand? Do they teach you the right hand rule in Math 6? What do? They do this one? Or they do the hand, the straight hand and then bend your fingers? That one? Okay. So the straight hand shake and the gun one are the same thing. They really are. It's just a question of how you want to hold your hand. I want to hold your... That's Beatles. Okay? For me, this shape hurts. I'm old, arthritis, all that kind of stuff, right? For you guys, I'm sure it's fine, right? So that's why I tend to go with the handshake. How do you do this? Okay? So the right hand... So, okay, again, with these two vectors that I've shown in green here as an example, what's the only directions that the answer could be in? In or out of the screen, right? There's the only two directions that are perpendicular to both of those vectors at the same time. Both of those vectors are lying in the plane of the screen. And if I want to be perpendicular to both of them at the same time, it's got to be out or into the screen. The only question is, which way is the correct way? The way you find that out is with the right hand rule. The way this works is you take your hand like you're going to handshake and you align it in the direction of the first vector, say this 60-degree vector here. Okay, we'll say that's A, right? So you're shaking in the direction of the 60-degree vector. You have been endowed with an incredible mechanical device called a wrist. Okay? It allows for quite a bit of rotation around an axis. So you're going to shake in the direction of the first vector and then rotate your wrist so that you can naturally bend your fingers in the direction of the second vector. I try to keep them straight. This isn't a hitchhiker where I'm curling up. But I'm shaking in the direction of the 60. I rotate my fingers towards the 90-degree angle. And which way does my thumb pointing? Out of the screen. So the cross product between this 60 and that 90 would be out of the screen. What if you were doing it the other way around? What if it was the 90-degree vector crossed into the 60-degree vector? How would you start your handshake? Straight up. And then again, you must rotate your wrist so that your fingers can come in the 60-degree direction towards the 60, and your thumb ends up pointing which way? Into the screen, right? So you get a flip-flop of the directions if you flip the order of the cross product. So be careful. Cross product is first vector crossed into second. You shake in the direction of the first vector. Turn your wrist so that your fingers can naturally bend in the direction of the second vector. Your thumb gives you the direction of the cross product.
So it's A times B, you would point it towards A first?
A first. So if I'm calling A my 60, right? So yeah, the order matters. Now, health and safety warning. If you are causing yourself physical pain while doing the cross, I've had students, you're bending your fingers the wrong way, okay, right? Rotate your wrist around. I've had students, I hurt my shoulder. Well, if you just rotate your body around a little bit, you'd be okay, right? Physical therapists are standing by. Mental and emotional trauma is normal, right? But physical pain should not be a part of the cross product. So just, again, if you feel like you're bending your fingers the wrong way, something's gone wrong, right? And you shouldn't do that. All right, so let's do some examples. I've got two examples here. We're going to do a lot more with the right-hand rule later. So let's just do examples involving vectors that have components to them. I wrote down 2i plus 3j plus 4k. Gee, I wonder where I came up with that vector. That was boring. All right, b equals 3i, oh, this is more exciting, minus 2j plus 4k. So there's my two vectors. No, Have you noticed how many dimensions all of a sudden we are working in? Cross product forces us into 3 dimensions. We can't cheat and just say there's 2 dimensions anymore. There's definitely 3. Okay, so how do I do this? Okay, again, I could just plug it into the red thing in the box, but I'm going to go ahead and use a little spreadsheet here, right? I, J, K. What do I write on the second row? What is A's x component? It's 2. And Y? 3. And K? 4. What do I write down on the third row? 3, -2, and 4, right? First step, get the correct components in, right? Okay, this is equal to I hat. All right, what am I going to cover up? Cover up the I, and then I'm going to do 3 times 4 minus 2 times, -2 times 4. Boy, that's a lot to hold in your head, so let's be careful. What's 3 times 4? Minus, and then what's -2 times 4? It's a -8. See how you got to be careful with your signs? Be really careful. Okay. Minus J, for reasons that Mr. Balogh said I shouldn't think about. Okay, so we cover up the J column, right? So what's our first multiplication? 2 times 4, and then 3 times 4, right? So 2 times 4 is 8, minus 3 times 4 is 12. Plus K, cover up the K column in my algorithm, right? So I'm going to have 2 times a -2. What's that? -4. And then I'm going to have 3 times 3, which is 9, right? -9. So assuming I did all that right, it's a big assumption. 12 plus 8, 20. Minus J hat, 8 minus 12, -4. Plus K hat, that's minus 13, isn't it? 9 plus 4. So what do I get? I get 20I plus 4J minus 13K hat as my answer, right? The thing in the box is guaranteed to be perpendicular to both A and B automatically. Okay, let's do another one. I'm going to do this in the context of torque. So let's say that we've got a force and we know that it's acting, say, in that direction, like in an XY direction. And I've got a moment arm that extends, say, with those components. Don't get hung up on the physics too much. Let's just follow the math, right? And what we're going to do is we're going to find the torque, which is R cross F, right? Okay. I, J, K. What goes on the first row? What's the first vector? It's R. So what goes on the first row? 2, 4, 0. There was no K component given, right? So we assume it's 0. Okay, on this third row, it's 3, 3, 0. Right? Okay, run the algorithm. Now, this is going to be pretty easy. Cover up the I. What's 4 times 0? What's 3 times 0? Ah! There's no I component, right? Okay, cover up the J. What happens? Yeah, they zero out, don't they? The only one that's not 0 is the K. Think about it. The 2 vectors were where? X and Y, X and Y. What's the only direction that's perpendicular to both X and Y at the same time? Z. So I'm going to have a K hat, and 2 times 3 is 6, minus 4 times 3 is 12, so this is minus 6 K hat. All right. I've shown you all of that, which is important to know. Over here, this right-hand rule, like a quick calculation of AB sine theta. That's kind of what we've been doing the whole time, where I told you R is perpendicular to F. Perpendicular meant sine of 90. Sine of 90 is 1, right? You're left with just R times F. I've been doing that the whole time. But what we're going to do is we're going to try and get in the actual directions for these torques, explain why that's important next time, and then get into angular momentum. Because angular momentum is also a cross product. I will see you tomorrow for moment of inertia. Remember, that lab is a pretty meaty one, so read up on it ahead of time and be prepared to stay in the lab for the whole time.